Today, we're building a bio-inspired salamander robot. It's cute, it's squishy, and it runs on Microfluidics. Last time we built this walker, inspired by a salamander. And it actually worked, kind of cute honestly. But why a salamander? Because they are like little time machines, still moving today like the first animals that crawled from water onto land, millions of years ago. The core of the robot is its leg mechanism. Simple in design, but already surprisingly complex in behavior. And if you've seen my snake robot video, you already know that it's powered by the same type of actuator. These soft muscles are called rolling diaphragms. I based the design on what I found inside a regular air pump. The actuators essentially work like soft cylinders. Push in air and the muscle stiffens. Pull a vacuum and it contracts. To manage all that air, I built this electrofluidic system, basically a bunch of diaphragm pumps and solenoid valves controlled by an Arduino. But one of my long-term goals is to make all of this more integrated. Like, imagine a PCB, but instead of routing electricity, you route air. That's microfluidics. Tiny channels that guide fluid and perform a function. I started experimenting with that in my last robot by printing microchannels directly into the body. But before diving fully into integration, I wanted to see how much more complexity I could push into the current setup. I found this CT scan online, and these are the little guys it came from. Zooming in on the forelimb, we see something familiar. There's a shoulder blade, an upper leg, and a lower leg. It's basically the same limb structure we have too. Now, if you compare that to my last robot design, well, we've got the shoulder, the upper leg, but no lower leg yet. So let's add that. And it would need to bend backwards. Last time I tried removing the legs entirely, and to my surprise, it still kind of walked. Some of you pointed out it reminded them of a starfish walking. If you look closely, some of the cylinders are not fully contracting, but rather bending. A single soft cylinder was the starting point. I extended both sides to give it a more leg-like shape. Trying to induce repeatable bending behavior, I came up with two variants for the lower leg. One with this internal structure built into the rigid base, and one where I reinforced the silicone wall. Let's find out if they actually work. I printed both molds, one for each version. The casting process is pretty much the same for both. Then it's time to mix the silicone. I filled it into a syringe. And here's a trick. If you plug the end and pull the plunger, it creates a vacuum inside the syringe. All the tiny bubbles come out. Once it's bubble-free and completely clear, it's ready. I injected both molds and cured them at 60 degrees on my 3D printer bed. After demolding the parts and carefully trimming them, they both looked promising. I printed the leg bases and hammered in these blunt needles as fluid connections. After installing the silicone, it was time to test them. And hey, the structured base works beautifully. The one with the reinforced wall, not so much. It just kind of tucked in on itself. Sad little blob. So I took the best of both worlds, added the reinforced silicone onto the structured base, and yeah, let's just go with that. Now that we have a working lower leg, let's connect it to the shoulder. So I redesigned the upper leg to link both the shoulder and the lower leg. The shoulder has 3 fluid inputs, one for each of the vacuum muscles. I added a fluid connection from one of those shoulder actuators directly to the lower leg. So whenever that muscle activates to pull the leg back, it also bends the lower leg. I printed the new connector piece and punched an extra hole into the membrane of the shoulder to route the airflow to the lower leg. With everything assembled, it was time for a first test. I hooked up a syringe and yeah, it didn't really work at all. I decided to add zip ties to all connections. Then I hooked it up to the electrofluidic system, hoping that it finally get moving. Now, the last time I found 3 basic motion patterns. Activating the muscles one at a time gave this triangular footpath. Pairs in sequence created a kind of star. And alternating singles and doubles made this almost circular motion, what I ended up calling the circular gate. So I applied that same circular gate to the new leg. It actually worked. The leg started moving, bending, stepping, exactly like I hoped. To understand the motion more precisely, I tracked it in Blender. The path looks great, but notice how the curve space isn't quite parallel to the ground. I will probably rotate the whole leg slightly in the final robot design. When you really look at it, a salamander is, to a surprising degree, just spine. Like it's almost all spine with some extras attached. Luckily, we have already built something spine-like, the snake robot. How do we combine the spine with the walker? Let's jump into CAD. I started out with our new leg design and rotated them slightly. Now I am bringing in the segments from the snake robot, 1 for the neck, 3 for the body, 3 for the tail. Then I added what I call the hip and shoulder blocks. The hip block has 8 fluid ports in the back, which correspond to the 8 outputs of the electrofluidic system. But how do we connect the hip to the shoulder? In the old robot, it was easy. It was just one solid rigid block. I needed something more flexible, something like a spinal cord. I designed this silicone connector with embedded microchannels. Printed a mold, inserted these wires from the side, and poured over some silicone. After curing, I carefully pulled out the wires. And there it was, a flexible connection with integrated channels. To show what's going on, I color-coded the internal volumes. What you are seeing here are all the internal air volumes. Now let's isolate just the ones that control the legs. You will notice I bundled the diagonal leg pairs together, just like in the last version. The assumption was that these diagonal leg pairs move more or less in sync. So to keep my robot light on control lines, I decided again to link diagonal legs together. Now let's talk undulation. As you can see, I only added 2 control inputs for that. But salamanders don't just walk, they swim. Water is kind of their true home. And if you look closely when they swim, you'll notice something interesting. Their entire body forms a traveling wave. It moves from the head down to the tail. And that's exactly how I controlled my previous snake robot, using 8 individual inputs to create that traveling motion. But when they walk, it's different. It's not a traveling wave anymore, it's more like a standing wave. The spine just swings side to side between 2 S-shaped postures. So, based on this, I designed the body to switch between these 2 mirrored S-shapes, morphing from one undulation state to the other. The 2 extra ones are just there to wiggle its face. To balance the robot's length, I added a passive tail. Did a mold with an insert. And poured in some silicone. After curing, I tried to remove it, but it was really stuck. In the end, I just broke off a chunk and out came the tail. And during walking, it should work as an extra contact point. And there it is, the full design. The Salamander's body is made of 4 materials. First, all the rigid parts are 3D printed from PLA. Then the squishy stuff molded from silicone. To connect everything, I use stainless steel capillary tubes for the air channels, plus a few small screws to hold it all together. And finally, zip ties made from nylon. Before the full assembly, I hammered in the capillary tubes. About 40 individual parts make up this squishy little creature. At this point, it was finally time to put it all together. And it's really starting to look like something. Next, installing all the zip ties. And finally, the spinal cord. It flexes beautifully. And I just love how wiggly this thing feels. With everything in place, I connected the robot to the electrofluidic system. In the last version of the Salamander, I developed this gate, and as a first test, I applied the same gate to the new design. It looked like it wanted to walk, but it just wasn't strong enough. I added a third vacuum pump, and more importantly, a positive pressure pump. Just a normal air pump. Just turning on the pumps, you could already see the difference. The positive pressure stiffens the actuators and lifts the whole body. And once I turned on the gate, it started to move. No undulation yet, but it was already walking. Looking at this mess of tubes and thinking about my long-term goal of full integration, I figured maybe it's time to simplify. So I designed a kind of chip, a 3D printed manifold that replaces all the tubing. It has inlets for the air pumps and connection points for all the valves. Inside, everything is already routed. I printed it in TPU so that the parts could just be press-fit. Then it was just a matter of pushing in the solenoids, giving them a gentle tap, and slotting in the pumps. Finally, I wired it up to the robot. Seeing the robot like this, I felt like it needed just a bit more personality. So I swapped out all the zip ties for bright orange ones. Because why not? And by overwhelming demand, I added googly eyes. I mean, come on, just look at that face. So cute! To keep the tether out of the way, I clipped it to my video light. And now, with everything in place, it's finally time to bring it to life. Real salamanders walk with this beautiful coordination of leg movement and body undulation. I found this fascinating study where researchers recorded muscle activity of salamanders during walking and swimming. And here's the surprising part. A lot of that movement doesn't come from the brain. It's generated here, in the spinal cord, by rhythmic neural circuits called central pattern generators. They even proposed a model of these circuits. But instead of replicating this whole neural system, I went with something a bit simpler. To control the rhythm of the robot's body, I created something I call the undulation function. It flips between two postures. Left, one of those S-shaped bands we saw earlier, and right, the mirrored S-shape. Just running this undulation function on its own already gives us this adorable little wiggle. The mid-trunk doesn't bend much while it's standing on the ground, but when I pick it up, you can really see it undulate. Let's add some leg movement. To control the legs, I use this muscle activation cycle I call the circular gait. Here's the trick. Every time the undulation flips from one side to the other, it triggers the next gait cycle. The undulation drives the gait. And like that, it started walking. Look at that tail go! By inverting the undulation function and reversing the gait sequence, it can even walk backwards. But what if we want to steer the robot? What I tried was to modulate how long the undulation function stays on each side. If it leans left for longer, it should curve left. And if it leans right for longer, it should curve right. That's a theory, at least. But weirdly, in practice, it does the opposite. When the body leans left longer, it curves right. And when the body leans right longer, it curves left. Why? Honestly, I don't know. Maybe you have a theory. Let me know. But hey, it still steers, so let's just go with it. To make it interactive, I connected a Wii nunchuck controller and mapped the different gait behaviors to the joystick. Let's try it out. Honestly, I'm kind of amazed how well this all came together. Watching this squishy little creature follow the joystick is just very satisfying. Of course, there's still plenty to improve. The leg friction isn't great. I could definitely improve the feet to get better traction. And the electrofluidic system, it's gotten kind of huge. And yeah, there are leaks. A lot of leaks. But stepping back for a second, it's kind of wild to think how far this has come. From a simple, soft actuator inspired by an air pump, to a slithering snake robot, to the first salamander walker, and now to this, a squishy, microfluidic, joystick-controlled robot with rhythmic motion inspired by biology. I'm really happy how this turned out, and the long-term goal still stands. I'd love to build a fully untethered, self-contained walking soft robot with the entire electrofluidic system, pumps, valves, even the logic all on board. And maybe one day, even a fully microfluidic nervous system, a soft robotic brain powered entirely by air. But for now, I'm really curious, how would you improve this squishy little creature? Let me know in the comments below. And subscribe if you want to follow the evolution of this and other squishy experiments.